So, good afternoon, everyone. Thanks for coming. And today I'm excited to tell you about Kvax, our open source FlashAttention implementation designed specifically for JAX ecosystem. My name is Sergei, and I'm a senior machine learning engineer in research and development team here at Nebius, and the author of Kvax. Before we talk about Kvax, a few words about Nebius. We are a technological company that provides full stack infrastructure for AI builders, GPU and CPU compute, networking, storage, and any kind of infrastructure you might need to train and run inference of your AI models, as well as fine-tuning and inference services. So what exactly Kvax is? It's a high-performance FlashAttention implementation for JAX, optimized to speed up large language models training, especially with long sequences. Let me highlight a few of its key features. First off, it delivers state-of-the-art performance for attention operation that involve document masks, particularly on long sequences. It's written on Triton, which makes it easy to maintain and extend with the new features. Plus, it includes out-the-box support for context parallelism, which allows to use it for training on very long sequences if you have the hardware. And fundamentally, it's built on the top of JAX framework. Okay, and let's talk about the why behind needing efficient attention. One of the things our research and development team is focusing on is training large language-based agents, in particular software engineering agents with reinforcement learning. And working with long sequences is essential here because agent-based system needs to rely on all previous steps to make the correct decision. But training with long sequences are very computationally extensive. To give you a sense of the scale, if you take a model like Qwen 2.5, 72 billion parameter, a single training step with batch size 1 and 8,000 token sequence length takes about 4 petaflops. But if you increase sequence length up to 65,000 tokens, the required compute increases to nearly 50 petaflops. This is a huge 12.5 times increase. But real-world data sequences aren't always the same length. And JAX, which requires all compiled function arguments to have static shapes, we typically handle this with two main ways. The first one is padding. You just pad the shorted data sequences up to the maximum sequence length. It's simple but very computationally wasteful because all pad tokens required compute resources without actually affecting the training process. The second approach is dense packing. Here you pack multiple data into one longer batch sequence. This is much better at minimizing waste, but does require some extra document mask during the attention operation to prevent different data sequences affecting to each other. All right, when we are dealing with long sequences, whether they padded or packed, FlashAttention algorithm becomes really important. Basically, it works by processing sequences block-wise, dividing in small blocks, and optimizing memory movement between different GPU memory types. This makes the whole attention computation faster and much more efficient compared to standard attention implementation. As you can see visualized on the slide, the attention weight matrix gets divided into these blocks. Also, standard FlashAttention algorithm can skip computing blocks based on the causal mask, which uses token position to prevent token attending to the tokens from the future. This optimization is called sparse flash attention and speed up computation even more. But there is a problem with a standard flash attention implementation when the document mask involved, because it processes the blocks that could theoretically be skipped based on the document mask alone. You can see them on the bottom left on the picture. This can lead to inefficiencies because ideally skipping those blocks could make the calculations even faster. And this is exactly where Kvax came in. Kvax solves this by precomputing all attention masks in advance. It helps to spot and skip the blocks that don't impact to the results without making, which makes the attention computation even faster. It's achieved using an additional Triton kernel that we designed to have low GPU memory footprint. Let's look at our example with the Qwen model again. With the 12 sequences packed together, Kvax cut the computational requirement by the factor 1.6, bringing it down to about 30 petaflops, which is a significant saving. To calculate the attention mask efficiently, Kvax classify all attention blocks into one of 4 types. The first type is the full blocks, where we do not apply any type of mask. The second type is left partial blocks, where only document mask is applied because of the start of the sequence effect. The third type is right partial blocks, where we both apply causal and document mask. And finally, the fourth type is the blocks that we could skip during the computation. We represent attention mask for each row query blocks with just 4 integers to encode the start and the end positions of these different block types. This compact representation allows for highly efficient mask processing within the attention kernel. Moving to another key feature of Kvax, context parallelism. Essentially, this technique splits the input sequence into chunks across multiple GPUs, allowing to process them in parallel. There are 2 main benefits here. The first is reduced per GPU memory usage for activations, which can help to avoid out of the memory errors. And the second is avoiding some sharding limitations of attention heads, which requires to be number of attention heads to be divisible by the number of shards. But there is a challenge. While most transformers operation can handle these chunks independently, the attention operation requires the whole entire sequence. So we need a specific inter-GPU communication to get the correct result. Kvax uses an efficient all-gather method, which is described in Llama 3.1 training paper. Here is how it works. Before the main attention computation, the key and value tensor shards are gathered from all GPUs. This means that each GPU temporarily has full key and value tensors replicated. Then each GPU calculates the correct slice of the output based on the local chunk of query and the full key and value tensors. And the great thing here that this approach plays nicely with the document mask. Plus, thanks to group query attention, the amount of data that transfers between GPUs is reasonable, leading to very low latency overheads, often negligible if the GPUs are within the same compute node. There is one more challenge with context parallelism, load balancing. When you combine context parallelism and causal masking, you run into the situation where some GPUs have much work to do than others. Specifically, GPU handling the end of the sequence need to process much more tokens than the GPU handling the beginning. And the problem here is that this imbalance slows down the whole attention computation, because faster GPUs end up waiting for the slowest one to finish. This slide visualizes that, showing that how the workload can be unequally distributed. And to fix this imbalance, Kvax employs a smart token permutation strategy, again described in the Llama 3.1 training paper. And the basic idea is, before processing, you conceptually divide the sequence length into 2 times n parts, where n is the number of GPUs involved in context parallelism, and then cleverly permute the tokens across GPUs. This permutation balances the computational workload much more evenly across all GPUs. This leads to faster attention computation overall. And the next slide visualizes how the attention mask with the causal and document mask combined looks like. In this example, there are 3 data sequences packed together. And on these slides, you can see exactly the same attention mask, but with a load balancing permutation applied across 4 GPUs. As you can see, the resulting pattern gets really hard for human to read, but the important thing that Kvax handle this correctly and efficiently. Kvax support different strategies, including both context and tensor parallelism. We manage that by using attention specification abstraction. This led the user to define how the different tensor axes, like batch or sequence, heads, or attention hidden dimension, should be sharded across your mesh of devices. This specification then automatically informs the internal shard map, defining how all inputs and outputs should be distributed. And this slide gives you a couple of examples. The first example for context parallelism, where we shard query by shard query tensor by sequence axis. And the second example is for tensor parallelism, where we shard query, key, and value tensors by attention head axis. All right, and let's move to some results. All our benchmarkings has been performed on H100 GPUs. And this slide shows that Kvax works faster than different attention implementation when the document mask is involved. If you compare Kvax to built-in JAX QDNN attention and PyTorch FlashAttention, in both forward and backward passes, you can see that Kvax comes out ahead. And the key insight from the left chart is that standard attention implementations like QDNN handle document mask less efficiently. Notice the increased latency compared to causal-only scenario. JAX is designed to avoid this overhead. Kvax also performs well on simpler causal-only scenarios, like processing a single unpacked sequence. In these cases, it outperforms alternatives like FlexAttention and standard PyTorch FlashAttention. It's competitive with, but slightly slower than QDNN implementation, which is highly optimized for exact this scenario. And the following charts illustrates how Kvax, blue and orange bars, significantly outperforms standard FlashAttention implementation that lacking efficient handling for document masking. green bar. Notably, Quarks with a context parallelism, blue bar, achieves competitive performance to Quarks with a tensor parallelism, orange bar, and both demonstrate a significant reduction in latency. And we are not standing still. Kvax is under active development. And for instance, we have added support for local chunked mask for Lamar 4 internally. This means it soon be possible to use Kvax for efficient fine-tuning of Lamar 4 models, leveraging its performance benefits. And now I'll try to anticipate a couple of questions that you might have. The first one, why did we build Kvax on JAX framework? Our proprietary training framework at Nebius is built on the top of JAX. And so Kvax naturally grew up from our internal needs. And we believe that JAX is a powerful and exciting framework for deep learning research. And we wanted to contribute something useful into its open source ecosystem. And the second question, why did we choose Triton instead of Pallas? We actually looked at both Pallas and Triton early on, and we ended up choosing Triton mainly because it's wider adoption. That's not to say anything against Pallas. It's very capable DSL, and we definitely keeping an eye on the interesting developments in this space, like Mosaic GPU project. And also, all Quark's code base is open sourced on GitHub, so you can scan this QR code to look at the code. If you want to dive deeper into the technical details, please check our blog post. There you can find more insights. And we are welcome for contributions and feedback. And one last quick thing, we are hiring at Nebius. So if you are passionate about development or JAX, writing high-performance kernels, or building cutting-edge agents, please check our open positions. Now we have 2 open positions, and we love to hear from you. And thank you very much for your time and attention. If you have any question, please don't hesitate to ask.
So I didn't get whether you're actually packing or padding in the end. So how are you really doing?
Okay, let me find the slide. Okay, this slide illustrates that the padding strategy is not really efficient, so we do not use it. And we developed Kvax exact for packing strategy, which we widely use in our internal needs.
Hi, I apologize. I missed the beginning of the talk, but I just was wondering, I was looking at your blog post, if you've just been using GPUs or if since you're already in JAX ecosystem, if you've tried TPUs and what your experience was using both, if you did use both.
No, we only use GPUs. It's written only for GPUs.
I see. Why, out of curiosity?
We work at Nebius, and Nebius the biggest provider of GPUs. So we have a lot of compute resources in GPUs. So we program everything for GPUs.
Great. Thanks. Again, apologies for missing the beginning.
No problem. Great question. Thank you.
Actually, there is a question about computation efficiency. Can I try it on my consumer card, for example, for small context, if I can? How is it computation? Is it computation efficient? Can you provide some numbers?
Depends. Yeah, thank you very much for your question. And I think it depends on your contact length. And I think for for example, for context length like 1,000 tokens, it's might work similar to the even standard attention implementation. But if we are speaking about context length like 8,000 and more and far more, then Kvax became really efficient in these cases.
Okay, thank you.
Okay, then thank you again. And if you want to talk about Kvax, please visit our booth. I will be happy to answer your questions. Thank you.